Hello and welcome to my presentation on Scalable SAT Solving in the Cloud. My name is Dominik Schreiber and I'm from the Karlsruhe Institute of Technology. Let me begin with our motivation. We want to take a closer look at massively parallel SAT solving and in particular at the popular large-scale solver Hordesat. So Hordesat achieved decent speedups actually for a lot of industrial instances, but on the other hand, in general, the more cores you invest, the less resource efficient Hordesat gets. So here we have a plot from the original Hordesat publication. We have the number of solved instances given a runtime per instance. So here we have the sequential baseline, and then here we see Hordesat's performance on 32 cores up to 2048 cores. And here you can see that going from 512 to 2048 cores, the difference is really negligible. So here you can really see that Hordesat fails to scale beyond this threshold of around 500 cores. So we're interested in the long-term perspective of SAT solving as a service. So having a cloud service for the resolution of propositional logic formula, and this may happen in an HPC environment in the end, where you have access to more than 1000 cores at a time. And also in such a system, you would of course have many users at once which submit their formula. So there's a need for job processing on demand, for dynamic load balancing and job scheduling. And also there's a particular need for low latencies and for quick response times if such a system is supposed to work well in practice. So our contributions are the following. First, we outline the framework Mallob for job scheduling and load balancing in the context of SAT solving. Secondly, we introduce the Mallob SAT Engine, also known as Mallob Mono from the competitions. So this is a scalable distributed SAT solver based on Hordesat. And then we combine these two to obtain a system for the scalable resolution of SAT jobs on demand. So let's first briefly talk about our system architecture. We're running our system in an environment where we have a number of physical compute nodes, and each of the nodes has a number of cores. So we group these cores into PEs or processing elements, and on the software side, each of these PEs is one process in the end. So these PEs can only communicate with each another via the so-called message passing interface, or MPI in short. And basically this means that any PE can send a message to any other PE at any time. Okay, so let's now take a look at how our Mallob system handles job scheduling and load balancing in the context of SAT solving. So for this, I have a little visualization of a grid running Mallob during one of our supercomputer runs. So each node here is one PE. And here you can see that right now there are 21 idle nodes, and we see in a moment why it's important for Mallob to have these idle nodes. And then there is one job in the system. So each job is arranged as a binary tree of PEs. And as you can see, the position of the nodes of this tree are completely randomized. But if I hover over the nodes, then I can kind of see the structure of the binary tree. So the largest node here is supposed to be the root, and these here are its direct children. And then, for example, this would be a leaf node, and we can see its path to the root. So how does such a binary tree get constructed, and what is its purpose? For this, I will forward the execution by a little bit, so on a quarter of the actual execution speed. So what we just saw now was a new job entering the system. So when a job enters the system via some external interface, then a job request message will randomly bounce through the system until it hits a PE that is idle and that is willing to adopt the job. And that's what happened right here. So now this is a binary tree of size 1. It only consists of the root node. Whenever a job enters the system, all of the PEs talk to each another in a lightweight manner. This is called a collective operation. And the result of this collective operation is that each of the root nodes, so these two in our case, have knowledge on the number of jobs in the system, as well as their individual demand for resources and their priorities. And on the basis of that information, each of the root nodes can compute the fair volume, so the fair number of PEs that are supposed to compute on that job right now. And if this job has computed its fair volume, then this volume update will be broadcast through the binary tree. And for example, if this new volume is 180 and it hits this node here, this leaf that has the binary tree index of 279, this is much larger, so the PE recognizes I should suspend my computation and leave the job tree. And that's what happens right here. So now this job essentially cut its computation volume in half, and now there is room for this job to grow. Here we can already see if a PE is supposed to have children within its job tree, but it doesn't, then it will again spawn request messages which randomly bounce through the system until they hit an idle node that adopts them. And like that we can see how this job expands, and now I will just leave it running. So we can see that this job expands to the same volume as the other job, but then the first job will already finish and the next one arrives instead. And like that we can see just how Mallob handles dynamically the number of jobs in the system and their load balancing. Okay, so now let's head on to the Mallob SAT Engine. So here I have a little table which highlights some of the most crucial differences between our Mallob SAT Engine and its precursor, Hordesat from 2015. So first, regarding the execution environment. In Hordesat, as in any other parallel SAT solver, or almost any other, the set of PEs is fixed when we launch the application, and then all of these PEs will compute on that formula, and this is rigid. For the Mallob SAT Engine, the set of PEs can grow or shrink almost arbitrarily during the computation. And this is a feature that is called malleability in the context of parallel algorithms. Regarding the communication, in Hordesat you have synchronous collective operations which are implemented and provided by MPI, where all of the PEs of Hordesat talk to each other in a regular fashion. In the Mallob SAT Engine we have completely asynchronous point-to-point messages, which in the context of a given job are always routed through the job tree, which itself, as we saw, is malleable, can grow or shrink. Regarding the core solvers, Hordesat uses a portfolio from 2014 involving Ling-a-Ling, which we updated to a new version, and now we also include a stochastic local search solver, YALSAT. Regarding the mode of execution, Hordesat, of course, spawns its solver threads within the main process, so within the process which also handles all the communication. Whereas in our engine, we can actually spawn the solver threads within a separate child process. And this allows us to seamlessly suspend, resume, or terminate solver threads at any time. And this is very important in our malleable environment, where a PE can leave or join or rejoin a job at any given time. We also included numerous performance improvements to our solver, which we won't detail here. So I want to detail one feature of Mallob, which is its clause exchange. And for that, to understand this, we first need to take a look at Hordesat's clause exchange. So periodically, so once a second, Hordesat performs a collective operation named altogether that is provided by all MPI implementations. For example, here we have 7 PEs which participate in this solving, and each of the PEs has a buffer of clauses which were just exported by the local solver threads. And these clause buffers are sorted by the size of their clauses. So the MPI altogether operation logically concatenates each of these buffers into one large buffer, and then this buffer will be broadcast to each of the PEs, which will then import the contained clauses to their solvers. This has a number of shortcomings. First of all, there may be a large number of duplicate clauses in this buffer. For instance, we can see the clause C contained here from the first PE, here from the fourth PE, here from the sixth PE, and here from the seventh PE. So we have 4 times the same clause, which is very redundant and unnecessary. Furthermore, we can have holes which carry no information whatsoever due to some of the PEs not completely filling up their buffer. And last but not least, as we can see, this buffer grows proportionally with respect to the number of involved PEs, which in our opinion constitutes a bottleneck with respect to the necessary communication volume and the local work necessary to produce and digest these buffers. So in Mallob, the clause exchange works via a custom collective operation over the job tree of a job. So here we can see 7 PEs as well, but they are arranged within Mallob's job tree. So whenever a new aggregation is to be done, then the leaf nodes in the tree will send up their clause buffers to their parent in the tree. And if an inner node has received as many buffers as it has children, then it will perform a multi-way merge of each of the present buffers, including its own local buffer. So like that, it produces a new buffer, and we can see this just works like a textbook multi-way merge procedure. So we would start with clause A here, then clause E here. We'll always take the shortest clause that any of these buffers has. Then this E, for instance, is already included from this PE here, so it will not be re-included in the result buffer. Then we head on to H and so on. So here we can see that we can detect duplicates immediately while aggregating the information upwards. So there's no need to sending around redundant information. And if we have this finished clause buffer at the root, then in a second step, this buffer gets broadcast through the binary tree to each of the PEs. So with this technique, we can also easily realize a buffer size growth that is sublinear in the number of involved PEs. So at each further level that we reach in this aggregation, we can just limit the factor by which the clause buffer may grow. And then we can just discard the clauses which did not fit in, which then are automatically the longest. So generally the clauses that are considered least useful. Okay, so now let's take a look at some evaluations. First, we wanted to see how Mallob performs regarding standalone SAT solving of single formula on our largest tested configuration, which is a 2560 cores on 128 machines. We selected 80 instances from the international SAT competition of the previous year because we are committed to running resource efficient and responsible evaluations in this expensive environment. We also fixed 300 seconds per instance, which in terms of core hours is roughly equivalent to the core hours attributed to each instance in the competition's cloud track. And we subdivided each machine into 5 PEs with 4 threads each. So here again we have the number of solved instances given a runtime per instance, so higher is better. And here we have a baseline which is just the original Hordesat, just with a couple of bug fixes. So then here we have the new portfolio which Mallob uses as well, and we can see that this brings a lot of improvement. So this is really beneficial, this portfolio update. And then here we have 3 configurations of Mallob. The first one, Mallob monoconst, involves that each round, so each second, only a very small constant size buffer is sent around containing clauses. So each second only around 1,500 integers are shared. And this is really not a lot. And you can see that this is highly detrimental to Mallob's performance compared to the other configurations. So this really highlights the necessity for meaningful clause exchange in such a solver. Then we have this prop variant for proportional. So here we grow the clause buffer size proportionally with the number of PEs, and this just emulates the clause buffer growth of Hordesat, where a lot of clauses are shared. And then we have a compromise sublin for sublinear, where we grow the clause buffer size in a sublinear manner with respect to the number of involved PEs. And in general, we found that this variant performed best. And then Hordesat has a mechanism where it limits, it imposes a limit on the LBD score, so the literal block distance metric of a given clause, in order to be shared. And if a PE does not completely fill its buffer, then it will make this limit less strict successively. And we found that for our solver, this mechanism is really not beneficial, but rather slightly detrimental to overall performance. So we continue with this any LBD variant, where we just don't impose any limits on the LBD scores of clauses. So now let's take a look at some scaling experiments. We compare the best Mallob monovariant with the best Hordesat variant. So if we have an instance F that was solved by a parallel approach, then we attribute to it a parallel runtime T par, which we kept at 300 seconds, and also a sequential runtime, which we kept at 50,000 seconds. So this is a baseline run of sequential ling-a-ling. And if ling-a-ling did not finish on an instance which the parallel approach solved, then we just attribute a runtime of 50,000 seconds as well. So then the total speedup is defined by dividing the sum of all sequential runtimes by the sum of all parallel runtimes. And the median speedup is defined as taking the median of each of the individual speedups, so the sequential runtime divided by the parallel runtime. Here we have some results. So here we have a logarithmic X scale with a number of cores, and here we have the speedup. And we can see that both for the total speedups up there and also for the median speedups down below here, Hordesat here with these squares really falls off if we go beyond 640 cores, which is really consistent with the findings from the original Hordesat paper. So we can see that updating the portfolio did not really help there in terms of scalability. Whereas Mallob scales very consistently up to 2,500 cores. So now assume you have all of the 400 formula of last year's SAT competition, you have the full cluster of 2,500 cores, and you want to resolve as many instances as possible while minimizing the average response times for each of the formula. What could you do in such a case? Well, first you could just run 400 sequential SAT solvers on 400 formula at the same time. So in this little idealized scheduling diagram here, we can see that we attribute each formula to one core and then we run them until they finish, right? And this is resource efficient because there is no redundant work that's being done. But on the other hand, it's suboptimal because not all cores are used. And also if one formula finished, then this core will just stay idle for the remaining time. The other extreme would be to run our massively parallel solver on each of the formula on the whole cluster and then somehow sort these runs. And we calculated an optimal scheduler which knows the runtime of each of the formula in advance. So that's a little bit unfair. So we just sort the jobs by their runtime in ascending order. And that would look like that. And then, last but not least, of course, we also run our Mallob system where we just introduce all of the 400 jobs at system start, and then we see what happens regarding its load balancing and job scheduling. So here we can see that as more and more jobs finish, like here F2 and F3, the remaining jobs, F1 in this case, receives more and more resources, which help to accelerate its resolution. And here we can see the results with the number of solved instances, given the total runtime of the system, and we can see that our Mallob solution actually outperforms any of these extremes and in the end solves most of the instances among any of these approaches. In conclusion, we've proposed a distributed SAT solving system that scales up to 2,500 cores. In HPC environments, we have seen that it is beneficial to combine the resource efficiency of parallel job processing with speedups obtained by a flexible degree of parallel SAT solving. In particular, we exploited malleability for low scheduling latencies and for quick response times for our system. For future work, Firstly, we would like to explore clause resharing strategies for malleable SAT solving, such that a PE joining a job late will still receive the information that has already been found before during the solving. Secondly, we would like to integrate further SAT solver backends, which partially already happened. And thirdly, we would like to add support for incremental SAT solving to our system, such that we can integrate incremental applications like from automated planning or software verification. Thank you very much for your attention.